Hello everyone, I am Panta Karimi and today I'm going to talk about our work on rate control for real-time video. As a student studying abroad, video calls are the primary means to contact my family. Now let me share a recent personal call.
چه خبرها؟ میگم یک بگو یک.
It is 2026, but we're still experiencing glitching videos, high latency, and crosstalk. And it's honestly very frustrating. Now let's talk about real-time video. The fundamental requirement of real-time video is very low latency target. And unlike Netflix or YouTube, there is no prior video to be prefetched, preprocessed, or buffer. So the system has to react almost immediately to network changes. Otherwise, the users will see freezes, glitches, or huge delays. And real-time video is not just about video calls. Real-time video shows up in cloud gaming, teleoperations, and even remote surgery. In this work, we present Vidaptive. Vidaptive is a responsive rate controller for real-time video, and we implemented it directly on top of WebRTC. WebRTC is the engine that powers many real-time applications such as Zoom, Google Meet, Teams. In our evaluation, we compared WebRTC and Vidaptive achieves 40% better video quality and 2.2 seconds lower tail latency. Now let's see how it works. Let me first show you how real-time video systems are structured today. On the left, we have the sender, and on the right, we have the receiver with network in between. The encoder and decoder are responsible for handling video packets. Congestion signals go into the congestion controller, which tries to estimate the link bandwidth. But here's the key detail. The congestion controller does not control the sending rate directly. Instead, it gives a target bitrate to the encoder. In practice, the interface is set up such that the video rate in the network is more or less up to the encoder. There is a significant body of research on congestion control algorithms, or CCAs. We have many good delay-based congestion control algorithms like COPA that are normal traffic. They keep delay small and throughput high. So the obvious question is, why do real-time applications still suffer? Why don't we just use the CCAs like COPA for video to keep the latency low and quality high? We were curious about this and we tried it. We replaced WebRTC's congestion control with COPA. WebRTC's congestion control algorithm is called GCC. This sounded reasonable, but the results actually shocked us. The latency increased drastically on average. So why does a great congestion controller completely falls apart when you run it on video? The reason is that the video violates the fundamental assumption that most congestion control algorithms have. Most congestion controllers are designed to work on top of a backlog flow, like a file transfer, where there is always data to send. Real-time video, however, is different. It comes in bursts, one frame at a time with silence in between. So instead of a full pipe, the congestion controller gets bursts and pause and then bursts and sometimes underflows and overflows. And during these pauses, the congestion controller loses its feedback signal. A broken feedback signal makes network estimation difficult. In a backlog flow, when the controller wants to send, let's say, 3 packets, the application provides 3 packets immediately and sends it, so the congestion controller gets its feedback. With video, however, the application may have fewer packets to send. So the congestion controller gets confused whether it was a congestion or it could have more packets to send, causing to more ambiguity. This ambiguity breaks the feedback loop, and that is especially problematic in highly variable links. such as the one I showed you the video, the real call that I had. The culprit is the video encoder. In this figure, we supplied the encoder with a target bitrate, the red line, and we measured the achieved bitrate in the blue line. When the target suddenly drops, the encoder needs a few seconds to catch up. It can overshoot, which causes latency spike, and it can undershoot, which breaks the tight feedback loop of congestion control. So even if you have a very good congestion controller that makes fast decisions, the encoder cannot execute at that time scale. To handle this discrepancy, there are two general approaches. One is to change the video encoder, such as the work Salsify, and the second approach is to fix the transport. Now, most of the literature focuses on designing conservative video-specific congestion control algorithms. We propose to fix the transport by reusing good existing delay-based congestion control algorithms. Vidaptive keeps the congestion controller exactly as is, and it adds an abstraction layer to absorb the effects of the encoder. That would make the video look like a backlog flow to the congestion controller. So how do we do it? Vidaptive restores the tight feedback loop signal by decoupling the congestion controller from the video. The congestion controller sends as it sees fit to estimate the link bandwidth, and if there is no video, Vidaptive generates padding traffic to deliver to the congestion controller. So the network always, so from the perspective of the network, this always looks like a backlog flow. And the congestion controller can work as best as it can. Now that the network estimation is handled, we have to do something about the encoder. We have to supply something to the encoder. Now, let's take a pause here to recap what we actually achieved. In the original problem, there is this number in the world called the network rate that the congestion controller wants to discover by setting a target bitrate to an unpredictable encoder. On the right, in Vidaptive discovers the network capacity regardless of the video, and then later tames the video encoder separately. That's the key win. Now, what should the target bitrate be? If the target bitrate is chosen very aggressively close to the link rate, it can cause high latency. And if it's too conservative, the latency would be fine, but the video quality would suffer. In Vidaptive, we chose to pick the target bitrate dynamically as a ratio of the congestion control rate that we estimate. This parameter alpha adapts to the variability. The user specifies the target latency, and Vidaptive adjusts alpha online to meet the latency. On stable links, alpha moves close to 1. Most of the rate will go to the video with very minimal safety margins. On highly variable links, or the times that encoder is showing a lot of variability, alpha drops, we leave more safety margins. This let us adapt to both network and encoder variability. Now, to show you how we do it, we pick alpha using a smart online algorithm to control the tail of frame transmission times. We picked frame transmission times because it's one signal that captures both the encoder variability captured in the frame sizes and the link variability captured in congestion control rate. We look at the distribution of recent frame transmission times. The red frames on the right tail are the very slow frames that capture high latency. And when the tail extends beyond the budget, we reduce alpha, which lowers the encoder rate, and that shrinks the distribution, pulling the tail back. We keep adjusting alpha until the tail just meets the latency. Putting it all together, Vidaptive cleanly separates the system into two parts: a transport layer that maintains a tight feedback loop to facilitate correct estimation of the link bandwidth as best as we can, and a video control layer that manages the latency quality trade-off of the encoder and tames the encoder to match the link estimation. We evaluated Vidaptive on a set of real and cellular traces on a set of 20 videos randomly selected from the YouTube. And we show against PCC and GCC, which are rate controllers in WebRTC, with GCC as the default, it has 2.2 seconds lower tail latency and 40% higher VMAF, which is a perceptual video quality metric. We also show that picking different latency target, the parameter P, we enable Vidaptive to have high latency quality trade-offs that could be used by different applications. And the trade-off we are covering is a better trade-off than what WebRTC's default congestion control algorithm, GCC, allows. We show that with the smart way that we're sending the padding traffic, it helps to discover bandwidth faster. Without padding, the controller is often blind during video silences. With the padding, video bitrate goes up by 35%. And importantly, the impact on the latency is negligible because the delay-based congestion controller is maintaining the network delay. To wrap up, we presented Vidaptive, a responsive rate controller for real-time video. Vidaptive reframes the encoder transport abstraction to decouple them. We show that we don't need new congestion control algorithms for the video. We can reuse the already existing one, and we can make the video compatible with the good ones we already have. Vidaptive adapts the video to variability online, both the network and encoder variability. We have built Vidaptive so it can be easily integrated in all the devices that use WebRTC. And we're curious about some open questions for future work, mainly the theoretical limits of how much padding we can send, are there ways to lower the padding, and things of that nature. Thank you so much for listening to my talk.